towards the 14th, in case you want to know holiday. All right, so I kind of wrote the rules for you, and we're going to write examples next to it, like real examples from all those functions that I gave you on Friday. But transformation, first of all, we have shifts. We can move our graph up, we can move it down, we can move it left, we can move it right. You need to make sure you know which ones do what. If you have a function and you add or subtract a number outside the function, it's going to shift that graph up or down. So x squared, I kind of like that function. If I wrote x squared plus 2, that means it's going to take that parabola and move it up 2 units. So if you know what x squared looks like, and you see that, you're like, oh, it just moved up 2. And if you know how to make the graph, then it makes it really quick to graph these. If you have a number subtracted outside, like the square root of x minus 4, that would take that square root graph and move it down 4 units. In Algebra 2, they use lots of h and k's, like k was always on the outside, and it moved it up and down. H was on the inside, and moved it left and right. This is kind of how we wrote it in pre-calculus, and so I'm writing it like this again. If you have a number added or subtracted inside the function, then it's going to move it left and right. And it's the opposite of what you think it should be, right? If you subtract it, you probably think that should move it back, but it actually moves it to the right. And if you add it, it moves it to the left. So you have to remember that it's kind of the opposite of what you want it to be. But I'm going to use the same functions here. We can do something else, but just to kind of show you the difference. If I wrote x minus 2 squared, notice how I put the minus 2 inside the square, or inside the square root, or inside the cube root, inside the absolute value. This is going to move this to the right 2 units. So it's going to shift it over. And if I said the square root of x plus 4, again, notice the plus 4 is under the square root, that would move that square root to the left 4. I just like using blue on blue ink. I don't know why.
Yeah, can I ask you where you get the sweatshirt? Because that was awesome. I'm really jealous of it, to be honest. I thought about taking it, but I just can't do it.
I think it's one of the children that I get off the bus at 3 o'clock. It looks small. I think it's one of the bigger. So I'm going to ask them today. If they don't claim it's in there, I'll say it for you. I think it'd be kind of snug on you.
Can I try it on?
No, because I think it's stretched out.
No, I won't.
It looks children's size.
If anything, I just won't try that hard to put it on. I'll do one of these. This side now.
Look at that size. I don't know.
Maryland's a pretty thin man. I think you get it.
It looks short.
I agree with that.
All right, so let's practice some.
That could be my beach shirt. That could be like Rocky.
On your unit test, there are some questions where you have to graph some different functions, maybe a quadratic, maybe a square root. And again, if you know the transformations, it makes things easier. If you don't know the transformations, then you just have to rely on the XY chart, pick enough points until you make the shape. But when I see this, it says use the graph of x squared to graph the following. So when I see x squared minus 3, automatically I think what's happening to that graph? It is moving down 3. So I'm going to actually graph both. I'm going to graph x squared, and then I'm going to graph x squared minus 3, just so I can show you what's happening here. You don't have to graph both on your paper if you don't want to. So those functions that I gave you on Friday, the library of functions, in pre-calculus I always talk about that over the years you've learned these functions over and over again, and so you should have this, like, if you think about that SpongeBob episode where he has the filing cabinet in his brain, like, you should have this file of functions that when you see x squared, you just automatically go to that file and you think, oh, that's a parabola, and I know that x squared, right, I don't have to make an XY chart, but you could. I know that it starts at 0, 0. I know when I plug in 1 and negative 1, it goes up 1. And then when I plug in 2, I get 4. So I go over 2, 1, 2, 3, 4. My graph's a little off because my lines were off. But I know that that is x squared. I call that the parent function. That you can do all these transformations from that parent function. You can slide it up, down, left, right.
Okay, so
No, right.
yeah, you like birds. That's what happens. Everything
the graph of x squared minus 3. So I basically took this graph and I just moved it down 3 units. If that doesn't make any sense to you, then you just have to make a correction. I don't know. Enough. Okay.
3 is good. 3 is good.
Okay.
Five is better. What if I combine transformations, like on number 2 here? What if I have a plus 2 on the inside and a plus 1 on the outside? Fair?
We go over to the left and up 1, then you made it.
Left 2, up 1. And again, if you know the original shape, then you can just say, I'm going to go over 2, up 1. And then I always know when I go over 1 from that, I go up 1. When I go over 2 from that, I go up 1, 2, 3, 4. Really great if I can cross this. Huh? This is not just going to be x squared, right? Absolute value, which are the v-shaped graphs, the square root functions, x cubed, all those graphs from Friday are going to show up as these. So let's look through the rest of the transformations and maybe graph a couple more. And then I want to show you this other thing that's on the homework that maybe also be on the unit test. Questions about left, right, up, down? We can also talk about reflections in my graphs or my equation kind of moves a lot. If you throw a negative inside or outside the function, it's going to reflect it over the x or the y-axis. What you need to know is which one. If you're not sure, you can always draw a picture. But if you have a negative in front of the function, then it's going to flip over the x-axis. And so is yours off-centered like mine here? I don't know why I did that. So if I have an absolute value and I threw a negative out in front of it, think about what that does. Normally absolute value, everything you plug in there, I'm going to keep this in blue here, right, is positive. So that's why we get that V-shaped graph. But think about if you throw a negative in front. Everything you plug in is still going to be positive, but then there's a negative outside. So it's going to make all the y values negative. So you get, if you graph both of them together, it kind of looks like an X. But you just need to know a negative out in front means that the y values are changing, so it flips over the x-axis. And I kind of did like an awesome one on this one. Instead of just doing the square root of x, I kind of added a plus 2 on the outside. But if you throw the negative on the inside of the function, notice on this one I put the negative underneath the square root, that's going to reflect it over the y-axis. Some graphs is not going to change, right? X squared is already reflected in the y-axis, so you throw a negative in there, it doesn't change anything. But a square root graph, it will change it. So let's kind of graph both of these just so you can kind of see what happens if I have a reflection and a plus 2 on the outside at the same time. What does a square root graph look like again?
Sideways parabola.
Sideways parabola. Half of the sideways parabola. Right? You can really pick whatever you want for a square root graph, but I always try to pick numbers that are going to be perfect squares. So if I'm going to graph this first one here, what does this plus 2 on the outside mean that that sideways parabola has moved? It's moved up 2. So if you know the shape of it normally, you can move it up 2. Again, if you don't know, or you just want to verify, since you don't graph square roots very often, pick some points. Normally when you pick the 0, you get 0, but we're adding 2 to it. So we would get 2, so it's moved up 2. What's the square root of 1? 1. When we add 2 to it, it's actually going to be 3. And let's just pick one more. Aaron Cole's rule of 3. If I plug 4 in there, the square root of 4 is 2. 2 plus 2 is 4. That was terrible. You need to make sure you know it's a sideways parabola. Mine kind of looks like a line, doesn't it? Oh, thanks. I was like, why does mine look so bad? I was just winging it. 4. Thanks. negative 0 is still the 0, so I still get 2. Can I still pick 1?
No.
I can't pick 1 anymore because I can't take the square root of negative 1. I can't graph imaginary numbers. So it makes you have to change your x values. You now have to pick negative numbers, which is what's making it reflect over the x-axis. So then I'm still going to get the same y values, but my domain has changed. And so I just want to kind of show you that I get the same thing, only over here. Oh, looks like a bird.
Is that how you used to make your birds too?
Yeah, I don't know. I don't think I really made birds that often.
I used to do that for my beach pictures. Or where they were in the sky.
The birds. The other type of transformation, which is not a huge part of this unit test, so I'm not really stressing that you memorize all these rules, but you do need to know that flipping it over the x or y axis, or moving it left, right, up, or down, that does not change the shape. It's kind of like just sliding it around or flipping it over. We call those rigid transformations because it doesn't change the shape. But we can also stretch or shrink your graph, stretch or compress your graph. Those are called non-rigid transformations. In geometry, you call those dilations because you're making your graph stretched out or compressed down. So if you multiply a number inside or outside the function, it's going to change it. I don't really care that you memorize this. The other ones I really think you should know, whether it's moving it left, right, up, or down, reflecting it in the x or y axis. But here the rules get to be a bit confusing, and what I'd really like you to just be aware of is know that it changes the shape. But here are the rules in case you really care. If you vertically stretch your graph, then you have a number multiplied outside the graph where c is greater than 1. So an example of that would be like y equals 2x squared. Where the 2 is not inside the square part, we would say that this is vertically stretched by a factor of 2. It's going to change the shape. It's going to make it look thinner, right? If you're going to shrink or compress your graph, like kind of squish it down, same idea, but now you have to pick a fraction between 0 and 1. So if there's a fraction like y equals 1/2 times the square root of x. Again, the 1/2 is not in the square root part, which is what makes it a vertical. Because it's less than 1, we would say that's compressing your graph to 1/2 its original size. Do I care that you know when it's a stretch and when it's a compression? I don't really care. I do care that you know it's changing the shape. And in pre-cal, I didn't really make you know that much, right? Because here's why. Because in horizontal, it changes. For a horizontal stretch, so now instead of going like this, we're going like this. Now the number's inside the function, and now it has to be a fraction. So that would be like the cube root of 1/2 x. That's terrible. Who would want to graph that? No. I don't want to graph it. The 1/2 is inside the function, which is what makes it horizontal. It's smaller than 1, which is what makes it a stretch. Barf. And a horizontal compression is when you take your graph and kind of squish it in horizontally, and it's inside the function, so it would be like, what's another function? Oh, absolute value. I was trying to think of a different one besides x squared. The absolute value of 3x, it's inside the function, and it's bigger than 1. What else is annoying about these is you could really look at one graph, and a horizontal compression could be a vertical stretch. Like it just, like there's different things you could do to make them different. So this is not on your unit test that much, except for maybe a graph, and you don't have to be able to explain it to graph it. You can just make an XY chart. So let's graph a couple of these so you can see it's not as scary as this kind of looks, and then we're going to do the last thing, which is on your unit test. Oh look, 2 absolute value graphs. I like vertical stretches and compressions better than horizontal. I don't know why, but that's why I picked these 2. These are ones where I would say maybe think about making an XY chart just to pick a couple points. even if you know the shape. Like, I know absolute value is a V-shaped graph, but just to kind of get used to what's happening here. Again, I'm going to make both graphs on here. I'm going to make the original graph in black. That's kind of the background, so you can kind of see what this is doing to your graph. So I'm going to graph this one in black. You don't have to graph it if you don't want to. But it is just that V-shaped graph of the absolute value of x. If I throw a 2 in front of it, I'm basically multiplying it by a factor of 2. I'm doubling the numbers that I'm going to get. And maybe you'll see what's happening here, that you don't have to make an XY chart every time. What happens if I plug 0 in here? Am I still going to get 0? Yes. What happens when I plug 1 in here now? Normally I get 1. What happens when I plug 2 in here? You get 4. Normally you get 2. What's happening to my y values? You're multiplying it by 2, which means you're going up double the amount that you normally would for every x value. But what happens if there's a 3 in front of here? It would triple it. If there was a 5 in front of it, you'd multiply by 5. So that's where you don't have to make an XY chart. If you see that. But XY charts are not that bad to do. So look what's happening to this graph. Right? It's stretching out, so it kind of looks thinner. So I've taken this and stretched it out by a factor of 2. Change the shape. Well, because it's a vertical stretch. We're taking it and stretching it out vertically, which is what I was looking at. We can also say, here's where I was talking about the whole horizontal vertical that annoys me. Would this graph look the same as this graph? I think it would, because if I plug 0 in there, I get 0. If I plug 1 in there, I get 2. Like, it would still be the same. Which we could say that this vertical stretch is the same as taking it horizontally and compressing it. Which is why people get confused about is on the inside of the outside. That's why I don't stress it that much. Because these are exactly the same graph. Now this one would be different as a stretch or a string because of this negative out here. The negative means what to my graph, remember? What does a negative out in front do to my graph? Flips it over the x-axis. So this one is vertically compressing it and flipping it over at the same time. You can just make an XY chart and you should be able to get the shape here. I'm going to graph the same one again. The one in the background. It would have been nice if I gave you like the real graph instead of the one you have to make your own points on. Yes. Just erase it. I know, I'm so mean because I print your notes out every day. What happens if I pick 0 on this one? Still get 0. We could pick 1 here. We're going to get negative 1/3. I say let's pick numbers that give me not fractions. 3 would be a great number because 3 times negative 1/3 is going to be negative 1. Think about normally on this graph when we went over 1, we went up 1 because we're compressing it, like making it shrinking down. We have to go over 3 just to go up 1, but because it's negative, we're going over 3 to go down 1. And if I pick 6, what would I get? And I'm not even picking the negatives because I know it's the same over here. If you're not sure, you can pick the negatives. But it's still a V-shaped graph, but it's like you're compressing it down, which is making it look wider. Like those funny mirrors that you look at. That's the fun house. Stretching and compressing. On the unit test, the only thing you'd have to do using these stretches and shrinks would be make a graph, which you can just make an XY chart for. But there is another part on the unit test from this section, and it's this last example here, which is looks like a big example, but it's just because I wanted to do lots of different things. And I gave you one like this on your homework. They give you this weird little function, and they ask you to do certain transformations, which means you do have to know the rules for transformations to do this, because there's not an equation for this. So first of all, I think it's important that we find some points on here. So let's just go through and kind of label the vertices here, because it'll help us as we go through these examples. Make sure you label those correctly, because if you mislabel them, it's going to mess things up. 1, 2, 3. I think this one over here is the point for 0, 2, 2, 0, 2, and negative 4. Negative 2, so I'm about to mess that up. Agree with me on that? I'm going to double page this just so I can see the original at the same time. On your homework, you're just going to have to make these graphs, like just copy down from the book. I know that makes it a little bit small, but you have it right in front of you, which was my hope. Okay. So if this is f of x, what are we going to do to all of these points if I'm going to do a plus 3 on the outside? What does that mean? Up 3, which means could I take these 4 points that I started with and move each one up 3, or kind of add 3 to each of the y values? Do you agree that that's going to give me that shape? That's how they can make you know these rules on the unit test, because if you don't know that means up 3, if you think it means left 3 or right 3, then you're going to get the wrong graph. And there is a question like this on the unit test. So I'm going to take these, I'm going to move them up 3. So negative 4, oh my gosh, I can't see this. Negative 4, negative 2, I'm going to move it up 3. 1, 2, 3. And 0, 2, up 1, 2, 3. And up 1, 2, 3. And 1, 2, 3. Which means the shape should not have changed. We just like slid it up 3. Which way over to? Plus on the inside means that you're moving left 2. Now that means from the original one, the x values are changing, and you should go back 2. Again, the shape shouldn't change. So move left 2. And that's where I think making the points makes it easier, that you can kind of just move those over. Questions about that? I do some extra ones in here. What does the negative out front do to your graph? It flips it over the x-axis, which means, you gotta kind of think about that, everything up here is going to go on the bottom, but this point's going to flip up and go to the top, so it's going to kind of flip it over. So see if you can do that one ahead of me as I work on this. So that's going to be this, so the y value change. Okay. What about 4, 0? Does it change if you flip it over the x-axis? No, because it's on the x-axis itself, which means it kind of looks something like that. And then the last one here, what if I gave you 2 different transformations in the same one? That means both the x and the y is changing, but it still shouldn't be changing the shape. So plus 1 on the inside means what? Left 1 and down 2. And I think, if I remember correctly, the one on the unit test is more like B. of being able to do that. So it's kind of just testing, do you know those transformation rules? So -4, this really hurts my eyes. I'm going to go left 1, down 2, 0, 2. I'm going to go left 1, down 2, 2, left 1, down 2, and 0, 4, left 1, down 2. That's not so bad, right? Okay. This is the last new information for our unit test. So tomorrow I'm going to give you kind of a list of things that you need to know how to do for the unit test, and I'm going to give you a good amount of review, but hopefully I'm going to talk a very little amount tomorrow so that you have class time to work on that review, because Wednesday I want to be able to go over it so that we can go over and make sure you understand how to do all of it, because that's our second unit test. Remember, there's only 4 unit tests and a final exam, so we'll be like 2/5 of the way done of our test after for the final exam. We'll be halfway through with information for this. So you can see the homework. Did I put the homework on your paper? 7 through 18 all seems like a lot, but it's matching. I think they're all like absolute value graphs and quadratic graphs, and you're matching the transformation. The annoying part is some is on the next page. You have to flip back and forth. If you have pencil and you want to kind of mark them off as you use them, I'm okay with that as long as you go back and erase it. But you're just trying to like match those up. There are 3 that I gave you to graph yourself, 39, 42, and 48. I said graph the parent function, but if you don't want to, if you just want to graph the new one, I'm okay with it. But I do want you to give domain and range, because on the unit test you have to give domain and range. And then 64 is just like our last one. So there's really only 4 problems you have to work out, because 7 through 18 are matching, but it really does check to see if you know the transformation rules. There aren't marks on 7 through 18, like they're just pictures, I think. Oh, there's marks. Okay, you can see that. So if you see a negative in front, you know it's flipped over. Go and see which ones, like, kind of use process elimination as you're doing that. Yeah, 64, you're just doing A through B.
Yeah.
Because there's like A through J or let me see if I can find it. Let me stop recording really quickly before I forget.